Hello students, my name is Pragati Misra. In our last video, we were discussing about cosets, which was very useful concept of the group theory. Today we will discuss a new topic that is known as index of a subgroup in a group. Students always get confused when they have to find the index of a subgroup in a group. So firstly we will discuss the definition of the index and then we take some examples. Now the definition is, let H be a subgroup of a group G, then the number of distinct right or left cosets of H in G is called the index of H in G, and it is denoted by G ratio H. This is the way in which we can denote the index of a subgroup in a group G. So firstly, I want to tell you that I have discussed about the right and left cosets in my previous video. So those who are new on my channel, they can watch my previous video of the cosets. And in that video, I have discussed clearly that what is the right coset or left coset and how to find the right or left coset in any given group. But today I will discuss a short trick by which we can find the index of a subgroup in a group, and that is very easy. So you can determine it without finding the right or left coset of a given group. So I am taking our first example in which we are taking the group G that I have taken in the set of in the video of cosets. So this group contains 4 elements and this is multiplicative group and it contains 1, minus 1, I, minus I. Now I am taking one subgroup of this group, that is 1 and minus 1. It contains 2 elements. So whenever we have to find the index of H in G, we denote it by G ratio H. This represents that what is the index of H in G. Whenever we have to find, we write order of G divide by order of H. So you have no need to find the number of distinct right or left cosets. That process is very long process. If you know about the order of the given group, then you can easily find the index of H in G. So firstly we write order of G divided by order of H. Now you can see the number of elements in any given group is called the order of that particular group. So order of G in this case becomes 4 because the number of elements in this group is 4. And if we talk about order of H, then order of H is what? It contains only 2 elements, so order of H is 2. Now if we find the index of H in G, then this gives 4 and this is 2. So 4 divided by 2, so index of H in G is 2. So I hope you find you got the index of H in G. Now I will take some more examples. In our next example, I am taking the symmetric group S3. It contains 6 elements. We all know about it. I have discussed it clearly, completely in my previous videos. So you can watch it there. And this is the subgroup of this group. I am taking 2 elements in this subgroup, that is identity, and the element of order 2, that is 1, 2. This is a permutation of order 2. So firstly, we have to find the index of this H1 in G. So and G is what? This is S3. So we write G index of H in G in this way, and our G is S3 and our H is H1. I am taking here it as H1. So index of H1 in S3. Now the order of S3 is what? How many elements are there in S3? 1, 2, 3, 4, 5, 6. So there are 6 elements. So we can write here order of S3 divide by order of H1, and there are 2 elements in H1. So order of H1. Now 6, because order of S3 is 6 and order of H1 is what? That is 2. So if we divide it, we get 3. So index of H1 in S3 is 3. So I hope you guys are getting it. Now I will take the next subgroup for the same group. I will take the same group S3, but I am changing the subgroup. So in our third example, I am taking the next subgroup, that is A3. This is called the alternating group for the group S3. So I am taking the second subgroup for the same group S3. In this case, if we want to find the index of A3 in S3, then how we can find that? We denote it by S3 ratio A3. This is the way to denote the index of a given subgroup in a group G. So we write it as order of S3 divided by order of A3. And what is the order of S3? There are 6 elements in S3, so order of S3 is 6. and order of A3, we can see that this is the set of all even permutations. We know about it that identity is always an even permutations, and every permutation of odd length is an even permutation. If we see the number of elements, 3 elements, that is the length is odd, so this permutation is even. Again this permutation is again even permutation, so this is the set of all even permutations, and this forms a group with respect to the function composition, and we call it as alternating group, and this is the subgroup of S3. So an order of this subgroup is 3. So or index of A3 in S3 is 2. I hope you guys getting the point, getting my point about the index of a subgroup in a group G. So this was the examples. Now I will take some more examples. So in our next example, I am taking a group whose order is 4. So order of G is what? 4, and order of H is 2. Now if we want to find the index of H in G, then that is very easy. That will be order of G divided by order of H. That is 4 by 2. So we are getting the index of H in G as 2. So I hope you guys are understanding. Now I will discuss a very important theorem of group theory, and that is for finite groups, and this is very famous theorem, and you should always remember it. This is known as Lagrange's theorem. So firstly we will discuss the statement of the theorem, and then we go for proof. So firstly we will see the statement of the Lagrange theorem. The statement is the order and index. We all know about the index. I have discussed it earlier. So the order and index of a subgroup of a finite group. Remember it always that whenever we talk about the Lagrange's theorem, the group must be a finite group. So this point is noted point that the order and index of a subgroup of a finite group G are the divisors of the group G. So if you don't understand this statement, you can always remember that order of the subgroup divides the order of the group, but the condition is that the group should be finite. Suppose you have a group and you know about the order of subgroup, then you will always see that the order of the subgroup divides the order of group. So now we will see the proof of this theorem. So let H be a subgroup of a finite group G of order n. That is, the order of the group G is n, and suppose that order of H, that is the subgroup that we have taken, whose order is m. That is, H contains m elements and they are of form H1, H2 and so on, Hi, Hj and so on, Hm. Now, if we define the set of all right cosets determined by the element A, then this contains the elements H1A, H2A and so on, Hia dot, Hja and so on, Hma, because in the set, in order to find the right coset or left coset, we multiply the any element of the group G with the given subgroup. So we are multiplying, so each element of the subgroup is multiplied with the element A. Now all the m elements of the Ha are distinct. These all elements of Ha should be distinct, because if they are not distinct, in that case we find Hia is equals to Hja for all I is not equal to j. In that case, by the right cancellation law, A get cancelled by A, and so we get Hi is equals to Hj. This implies what? That every element of the group is same. So this is a subgroup is same, so this is a contradiction, and so we always take that Ha contains m distinct elements. Since G is a finite group of order n and H was also a finite subgroup of group n of group G, then number of distinct right cosets, that will be the index of the subgroup H in G, so that will be also finite, say k. So in that case, if we find G ratio H, that is the index of H in G, that will be k, a finite number k. And what is the index of H in G? We know that this is equals to order of G divided by order of H, and that is equals to k, and we have order of G as n and order of H is m, and that is equals to k. This implies n is equals to m into k. From here, what can we conclude? That the order of the group is k times of the order of the subgroup. order of the group is k times of the order of the subgroup. It means that order of the subgroup divides the order of the group. So from here we can write, therefore m divides n and k divides n. So either k divides n or m divides n. So if m divides n, then m is the order of the subgroup and this is the order of the group. So from here we can say that order of the subgroups divides order of the group, and this was the Lagrange's theorem. So I hope you guys are getting my point, and I hope the Lagrange's theorem is clear to you. And if you are liking my content, please subscribe my channel. Thank you.